All right. Well, hopefully you've watched the video about sample proportions. Basically, we did all the inference techniques there are with proportions. That included one and two sample intervals and tests. Now we need to move on to doing the same kinds of confidence intervals and tests for means or sample averages. Now, if we were still in school, well, we would have went back to the box. So pretend we're back to the box of paper slips. And we've got two important questions. Number one is, what's the average year in the box? Number two, does anyone in the box have the coronavirus? Good news is the box doesn't have any people in it. They're just slips of paper. So answer to question two is, no one in the box has any coronavirus. Glad that's out of the way. All right, let's go back to the other question that takes a lot longer to answer. What was the average year in the box? Now, you might remember me telling you the composition of the box, but I probably shouldn't have told you that, so you could have found it yourself. But it was good I did, because obviously you can't go to the box and do the experiment. So what would I have had you do? To find the average year in the box, basically I would have had you do like you did before, take out slips of paper and see what the sample averages were. And you have done this over and over and over and over again. Now, when you did the proportions, I had you take out slips of 20 because it was a little easier to get what proportion was under the year that I asked. The year I asked was 1960. To get an average for each sample, if I would have made you take 20 slips, that would have taken a really long time. So I would have knocked it down to 10 slips, but still would have been a bit time consuming. So what I would have had you do with the box one more time is I would have had you get in those same groups, and you basically would have pulled out 10 slips at a time, but you would have had to find what the average of those 10 slips were. So if you would have pulled out 1946 and 1952 and 1997 and 19 and so on, you have had to take those 10 slips, add them up, and divide by 10 to find out what the average year is. You would have got an average year for every time you took 10, and you would have written that down. Those would have been your, what would be called a sample average. You took a sample and found its average. Now you would have gotten different sample averages. Some would be higher, some would be lower. But once again, intuition would tell you that, well, if you're going to pull out samples of the box, chances are the samples average will cluster around the actual average of the box. So the box clearly didn't have an average of 1940. It would have been rare to get a sample average of 1940 because the box's average itself wasn't 1940. Now, is it possible? Yes, you could have got an unlucky sample, but you would have had very few slips that were far away from the box average, and more groups of your slips would have been, their average would have been close to what the box average was. And once again, this would be doing it with 10. Now, since we're not actually doing it, I could just pretend it, you would have taken 20. But basically, since we can't do this experiment, I'm going to show you last year's results. And basically, you would find what you'd expect, just like we did with the proportions, that the sampling distribution, the means, comes out in a shape that we recognize. All right, so what was the average year in the box? Well, let me show you the results from last year. So luckily I kept these. They ran the experiment. They basically took 10 slips of paper out over and over and over and over again, and they calculated the average that they got. I then, when they were done, had them place their average in one of the categories, basically in each block, from that, this would be 40 to 45, 45 to 50, 50 to 55, and so on. Basically, if their average fit in one of those categories, we'd count it. And these were the results that we got. Now, I was so confident because, remember, the lowest year in the box was 1930, and the highest year in the box was 1999. I was so confident that that no one would get an average of 1990 or an average of 1935 or something like that. I didn't even put them on here. So would it have theoretically been possible to pull out a sample and get an average of 1990? Yeah, it would have been theoretically possible, but basically no one's ever done it. And I guess, unfortunately, thanks to coronavirus, you guys don't get the chance to try to do the impossible, but chances are you wouldn't have done it either. So looking at the samples, there was actually only one group last year that got a sample average that was between 1940 and 1945, and that in itself was rare. There was nobody who got a sample average between 40 and 50. There was nobody who got one over 1980. So with the exception of this one outlier, which was pretty rare in itself, pulling out groups of 10, all of the averages were from 1950 to 1980. And then notice that where were most of the averages? Well, they were centered in the lower 1960s and upper 1960s. Basically, from this information, you could probably surmise that the average of the box was actually 1965. And notice it's not perfect, but most of the samples are within that range, right? Since the box has an average of 1965, most of the sample averages of size 10 came out somewhere close to 1965. The farther you get from 1965, the fewer that you get, and eventually get to the point where they completely die out. Now, since the sample size is only 10, the histogram is this kind of blocky thing. But notice it does have that classic unimodal symmetric shape. It comes out normal. Now, if we would have done a higher sample size, say I had you do the sample size of 20 or a sample size of 50, this thing would look more and more and more normal. So the higher the sample size, the more normal this looks, just like with the proportions. But we're not doing proportions this time, we're doing the average. So basically, what was the average in the box? You could use sample averages to figure it out. So if you took samples of size 10 or size whatever over and over and over and over again, you would find that most of the averages had the average of the box. And the farther you got from the average of the box, the less likely you were to get a sample of that type. All right. So this is the same kind of pattern, but this is what we call sample means. We're looking for an average in the population using the average of our samples. This makes a sampling distribution of the averages. So basically, as you pull averages of a certain size out of the box, what do they look like if you do it over and over and over and over again? You get this normal curve, and basically it's centered around the box's average. So the average of the sample averages is the population average. It's a lot of averages going on there, but we'll talk about it in more detail in a moment. And like with any normal curve, the mean of your samples was the mean of the population of the box. We need a formula for the standard deviation so we know how quickly this dies out. All right. So unfortunately, you guys weren't able to come up with the same results. Maybe if we get back in time, we'll have the course done. Maybe we could just do it for fun. But until then, we'll just have to use last year's results. So basically, I've done this quite a number of years now. It's always come out this way. Like I said, I didn't rig anything. I would have done the same thing where I was shaking the box and you would have taken out samples. All right. So with this in mind, we can also use this normal distribution to not just do sample proportions, but to do sample averages. All right. So the goal here is to be able to analyze sample means and the sample distribution, the sampling distribution that comes from sample means. So basically you have a population, you're going to take samples of a certain size out, and we want to know how likely we are to get a certain average based on the population average. So some of the nuts and bolts of this, basically a sample mean is obtained when the average of a sample is taken. So what you would have been doing with the box is you would have been taking out 10 slips, and you would have taken the average year. The average of your sample is referred to as X bar. So the little bar, remember, means the mean or the average. So the sample average is called X bar. You would have found lots and lots and lots of X bars. In fact, that's what they were doing here. this is a tally of all the X bars they found of sample size 10. What we would have found from our exploration that I just explained to you would have been what's below. As we find more and more sample means, the quantities of these will center around the population mean and be normally distributed. So basically the result I just showed you. Oh, nothing else is there. Let's go on. All right, so finally, they give a fancy name to this property. It happened with the proportions, but they really like it with the mean so much that they gave it the name the central limit theorem. So if you see this term, they like to test it on the AP exam and in statistics in general. This is referred to as the central limit theorem. It's also called the fundamental theorem of statistics. For you guys who also take calculus, you remember the fundamental theorem of calculus. And anytime there's a fundamental theorem, it's a really big deal. So this thing, like I said, it goes by two names. Some people call it the fundamental theorem of statistics because it's that important. It's also referred to, the AP exam is more likely to call it the central limit theorem. So what the central limit theorem says is basically what you would have found about the averages in the box had you been able to do it. Basically, it's what I just told you, like what they did last year. So it says, the central limit theorem says that the distribution of sample means can be thought of as a random variable that, with enough trials, approaches being normally distributed. So basically, the more means you take, if you took all possible samples and averaged them and did their distribution, you'd basically get a normal distribution. The key thing with this is that this will happen on any data group. It doesn't matter how the original data is distributed itself. So any group of data, so any population that you have, if you start taking sample averages, this normal curve of their sample averages, the way they're distributed, will appear. So this will happen on any data group so long as there's independence and randomization of samples. And those are conditions that we're used to having met. So another thing they like to test is that the sample means will be normally distributed regardless of the original probability distribution. Now, I think I've mentioned this before in class, but I didn't include the picture in the slide, so I'll show you in the book. I would have put this up on the camera, so I'll hopefully be able to get my camera here to show it to you. Basically, I did this example where I showed like what would happen if you rolled more and more and more dice. So if you just roll one die, the distribution of one die being rolled looks like this. It's uniform. So basically you have an equal chance of getting a 1, a 2, a 3, a 4, a 5, or a 6. Now if you start doing averages, so say you roll 4 dice and you take the average of what you get. So you basically just add them up and divide, or you could just see what their sum is. Basically, the average that you get starts looking normal. So they illustrate this in the book. Hopefully I can get you to see it. So let's see. Here's the book. All right. So they actually did this out. That's why it's not perfectly even. They actually did an experiment where they had a computer do this. But basically, here's one die. If you go up to 2 dice, here's the average of the 2 dice. So basically, they add them up and divide by 2. Notice it's kind of a staircase, or like a pyramid, I should say. But it's definitely not flat anymore. If you go up to 3, you get... I'm in my own light here. Notice the average of 3 dice starts looking a little more normal. Now, there's the average of 4 dice. I have to turn this. Where is it? Oh, there it is. There's the average of 4 dice. And that green thing... Oh, this is really difficult. The light green one shows the average of 20 dice, and the point is it gets more and more and more normal. This is that central limit theorem. Oh, so that was kind of annoying, but Hopefully you get the idea. All right, let's move this back over. So the sample means will be normally distributed regardless of the original probability distribution. So they kind of test this. The original distribution, if you just roll one die, comes out like this. But if you take a larger and larger sample, it turns out that the averages, the distribution of your averages, looks normal. So you would get a normal distribution. So say I rolled 50 dice. The average roll, if I averaged up all the, added all the numbers of the dice and divided them by 50, most of my results would come around the average, and very few would be far away from that. So even though the original distribution could look like anything, the sample distribution of the averages with a high enough sample size always turns out normal. All right? Hopefully that makes some kind of sense. In order to use a normal distribution, we need certain assumptions met, just like with proportions. So with proportions, we had to have independence, randomness, and we needed the sample not to be too big or too small. So we didn't want to take more than 10% of the population, but we needed it to be large enough, so we did n times p and n times q. Now, there are a whole bunch of conditions for this as well. They're very similar. They're not all exactly the same because, like, in this case, we don't have a p and a q, so we'll have to come up with some modifications to those. But basically, this says the necessary assumptions are very similar to the sample proportions. We need independence and randomness, and we basically need our sample size to be large enough. We'll talk about those in more detail, but just realize that in order for this to occur, certain conditions have to be met, just like with proportions. All right, so almost done with the all technical stuff here. So this is a little tricky, so let me hopefully convey this to you in a way you understand. When we get our sample means distribution, it's going to look normal, just like what I showed you that they did last year. Now, we're talking about a lot of different averages, so keep in mind there's your sample average, there's your population average. What the central limit theorem says is that your sample averages, if you average them, they should turn out as your population average. So it's a little confusing because there's a lot of averages going on, but basically the idea of the central limit theorem, one of its tenets, is that if you averaged your sample averages, they would become the population average. So when we go to make that normal curve, the normal curve's average, which should have, and the normal curve's mean should be the mean of the population. So it says the sample means will center around the population mean. What this says is that the average of your samples should be the average of your population. Now, the X bars used for sample means this Greek letter mu, it's like a U with a little extension on it. This is the Greek letter mu. This stands for the population mean. So it's basically saying if you took all your sample means and averaged them, it should basically be your population mean. So if I went back to the box, you would have gotten lots of different averages. Most of your averages would have been close to the box average. Now, say we would have done in class 300 sample averages. If I would have taken time to average all of the sample averages, it would have been almost dead on the box average, and the box average was 1965, right? So most people's sample averages would have been around 1965. Some of them would have strayed, but the average of all of them would have come out essentially as the box average, all right? So once again, there's a lot of means and averages going around. Hopefully you realize what that's saying. It's the average of the sample averages is the population average. Now, we also need, once we get that normal curve, we know its center should be the population center. What should its standard deviation be? Well, the means vary less than individual values. So if you average a group, they vary less than individual values. So basically, if you would only take out one slip, it would vary a lot. If you averaged 5 slips, it would vary less. You would have averaged 10 slips, which would have varied less. And if you would have pulled out 100 slips, the averages would have varied even less. So basically, the way to think of this is that, means of a group vary less than individual values. So think of like a class average versus an individual student average. Students themselves will vary more than the entire class. So, for example, amongst students, it's uncommon for some students to have an average of, failing 50, 60, and other students to have an average of 90 or 100. But when I look at my class averages are very